the ladle via the so-called tun dish in the mold of a continuous casting machine. The liquid steel starts solidifying in an oscillating water-cooled mold. The solidifying shell is cooled with water from the outside, and the completely solidified strand is continuously withdrawn from the caster. From the solidified shell, the so-called slabs with a length of approximately 12 meters and a weight of more than 20 tons are cut off with a so-called torch cutting machine. On the left picture, you can see the slab on the crane with an average temperature of 1000 degrees. And on the right, you can see the typical mold of a continuous caster. You can see that the liquid steel flow is controlled by the stopper rods, and you have the submerged entry nozzle in the mold here, and you can see the flow pattern where liquid steel is induced, and the liquid steel goes towards the narrow phase and up to the top, and you can see these fine bubbles here, which are argon bubbles. We use this argon to avoid clogging for carbon steel grades. So let's look at the casting platform, which looks really a little bit different in terms of what can the operator really see. So here you can see a typical picture of the casting platform of a continuous casting machine. The is in the front of the mold. The oscillating mold contains liquid steel with a temperature of approximately 1600 degrees Celsius. The continuous casting machine is operating almost fully automated on levels 3 and 4. The operator can only detect slight movements of the pool level in the mold visually. You can only see a small window if you're standing on the casting platform of the top mold. Fact is that we have to understand the behavior in the mold precisely to further improve slab quality and process performance. So the main questions are, what's happening in the mold? You can see more or less nothing. You have harsh environment, hot temperatures. So what to do? And the core question is also, what is the behavior of the liquid steel in the mold? How can we analyze the fluid flow in the mold, and how can we improve slab quality? The first possibility you can see here is doing experimental simulations with water models. Why can we do this? You have to notice that the kinematic viscosity of water at the temperature of 20 degrees Celsius is similar to the kinematic viscosity of liquid steel at the temperature of about 1600 degrees Celsius. You can see here a two-phase flow. We need water-air behavior, which is quite similar to argon and liquid steel behavior in the mold. And you can see these nice details, what we are looking for, especially if you look at the meniscus. And you see the highly turbulent flow behavior. And we need here full-scale water models where we get the Reynolds similarity and also the Froude similarity. And we can quantify these flow patterns with so-called particle image velocimetries. So we get really on different slides, we can figure out and really squeeze out these velocity amplitudes and also the direction. So the application area of this water model is a quick visual analysis to get the first impression from new phenomena. We have a fast characterization of flow behavior because of excellent instrumentation of the mold. We can develop, of course, also new measurement methods which can be used directly on the caster. And we use these water models to verify results of numerical simulations. And we will validate, of course, these numerical simulation models such as turbulent flows also with this water model. So it is a very nice first possibility to learn more about the behavior of the liquid steel in the mold. But the water model is definitely not enough. We also need 3D numerical simulations of unsteady, high turbulent, gas-loaded, partly loaded, including solidification, including free surface flow, and also including electromagnetic forces. And the big advantage is that we get details and results about velocity, temperature, and so on at any position of the calculation domain. The disadvantage is that the numerical CFD simulations take a long time and use enormous computing power. We are doing these research activities since many, many years successfully with the Institute of Fluid Mechanics and Heat Transfer of the Johannes Kepler University. So we have now the water model, which is very nice to get first impressions, to quantify, which is perfectly instrumented. On the other hand, we have this kind of high-level numerical simulations, which we are doing with our research partners. But this is not all, because we have to transfer all the results we get here directly to the plant. And this is the next step I would like to show you. So this transfer is necessary in the first step to do so-called industrial plant trials, where we check new process set points, and we also check the slab quality with these new set points. In the final stage, of course, we have to integrate this knowledge in the casting process in terms of mathematical models for process and quality monitoring and control. These process models range from data-driven models via semi-empirical models and physically based mathematical models. But most of these models we can see, and we are using here or implementing here, are so-called hybrid models, okay? So in this content, I remember a nice discussion we had last week, because on the one hand, we need reduced order models for advanced process control, which have to be all these phenomena in the mold. On the other hand, we need more and more complex models to describe the flow behavior in the mold more precisely, with millions of finite elements and weeks of calculation times. So what is the right way to go? The answer is that we need both directions. So this knowledge-based working procedure to further develop process performance and product quality is the here presented methods and tools as a long tradition in steel industry. And let me lift this picture to a more general and more trendy maybe application, what you can see here. We can see the 4 phases of connected, developing phases, which are really permanent in interaction. It is similar to a closed loop, let's say, innovation cycle, something like this. And you can see on the left, let's say the water model is more or less our experimental twin. And then we have this really complex numerical simulations, which is more or less, not more or less, it is definitely also a numerical twin representing the CFD simulations. And it is very important, this industrial scale-out, which is really need a huge experience for doing this. And finally, we have this industrial implementation to further strengthen our technology leadership, of course, and the quality excellence. So this is more or less a general picture where I believe that these 4 phases are necessary to succeed also in the future. So based on this, let's say, extensive knowledge we have about industrial processes and about methods for modeling and simulation, we have also to think about what could be the next level decision support systems. And we are, I think, in an excellent position to think about possible next level approaches and what can such a development look like. Here you can see a first scenario for a next level decision support. The first possibility could be the transfer of CFD results into the process control room directly to the operator. We've heard that these numerical simulations can take a long time and are far away from real time. But the results of these calculations include important informations which are also interesting for process engineers and quality engineers. So we have to transfer these relevant CFD results to these experts. Before doing this, we have to automate the workflow of CFD simulations, starting with pre-processing, then the simulation phase, and afterwards the post-processing. Together with my colleagues or our colleagues, we have to define the right key performance indicators, what they're interested in and what is necessary to bring them in a better position to make better decisions. And finally, of course, for data transfer, for all this data visualization, we need our IT experts who are doing this more or less, and where we have these channels for the workflow which are open for transfer these results towards the control room and to the experts on the plant. So these calculations can be done 24/7. This should be no problem. And yes, it's really the...
Alle 4 c'è una riunione con...
Hello?
C'è una riunione...
Okay. So this is one possibility. The next possibility I would like to present is something what you could maybe expect, and this is that we also take these nice solutions we get from the water model. And these quantified flow situations, we can correspond also with the current situation directly on the plant, and we can bring this information directly also in the control room. So maybe a short conclusion: the transfer of results of complex simulations to experts is very important. It can be one possibility for a next decision support system. Then this knowledge we have about this, we have to transfer it out, let's say, from the R&D department in our processes to our experts. And it is really important to guarantee this data transfer and the integration in the existing IT architecture, IT systems. So the next topic is smart logistics and transport. So this has been only a few words, a few thoughts about production processes. On the same level, important, let's say, are also logistics and transport. And logistics and transport processes are the connecting processes between our production plants. At voestalpine Steelworks, heavy transporters with a load of up to 100 tons travel several 100 kilometers a day on streets and gravel roads. Hundreds of slabs must be moved to the right place at the right time for further processing. Production planning, as well as transport and manipulation processes, must be perfectly orchestrated in harsh and dynamic environment. I would like to start with a slab transport optimization problem, which you can see here on this slide. You can see on the left, the slabs are produced by several continuous casting machines and are stacked by a crane within the so-called hot slab storage, what you can see here. From the hot slab storage, the slab can be directly transported to the hot strip mill here on the right, or they can be directly transported to the slab yard, or to the slab finishing, where we can repair them. In the middle, you can see also the trucks. We are using the truck trailer here on the and the straddle carriers we are using, and also for stacking the ridge stackers here on the top. Up to this point, you can imagine that if everything runs smoothly, everything runs perfect in the whole system, systematic planning of the transport jobs should be possible. But what happens if there's an unexpected stop of a continuous casting machine? If the quality control system identifies during casting slabs with quality problems which have to be repaired, if there's a breakdown of a heavy transporter, if there's an unexpected crane defect, or the hot strip mill stops. So these are disturbances acting on these transport systems which have to be handled. And this mastering is really a real challenge. And to master these extraordinary challenges, we also need excellent scientific partners, like the researchers working at the Adaptop Resselzentrum. And the research activities of this Resselzentrum are focused on adaptive optimization in dynamic environments. This is quite typical. The situation was what I described is quite typical for the boundary conditions and the application and of these solving solutions and methods coming from the Adaptop Research Center. The Research Center is located at the Software Park Hagenberg, and the scientists around Professor Stefan Wagner, who is the head of the center, will be present at the conference with some exciting presentations. Their research activities are focused on modeling on dynamic problems, development of reactive optimization methods, development of proactive optimization methods, and development of adaptive optimization methods on systems. Let's look at the next example, which could be also quite interesting in research and development. And this is about the integrated continuous casting and hot rolling scheduling. It's about production planning. Production planning of the steel plant here on the top and the hot strip mill here on the bottom on the left side. We started these research activities for the optimization and further development of the production scheduling systems about 5 years ago, together with the Department of Information Systems, Production and Logistics Management of the University of Innsbruck. The main goals are overall online optimization along the entire production chain, a full online transparency of all production lines, and a high precision in decision-making processes. The challenges have been to rethink working practice of these production planners, what they are doing, to develop real-time capable optimization algorithms, and to integrate the tacit knowledge of the shift schedulers. The result for continuous casting scheduling for a single process, for real-time continuous casting scheduling, is that we could get a perfect connectivity, data connectivity, which is the base for the further developments. And the casting planning in the steel plant was accelerated by a new algorithm, a factor of 100 approximately. So what you can see here is the research activities for a fully integrated midterm production scheduling. Midterm means about to plan or schedule the production within the next 7 to 10 days approximately. And this orchestrated between the steel plant and the hot strip mill. I remember very well what our scientific partner said at the beginning of the project. He says, it is remarkable that there are no publications on production planning in steelworks, in particular on the coordination of continuous casting and hot rolling for at least 15 years. So there's still a lot of research needed, of course. And here you can see the solution approach developed together with our scientific partner. It is a 3-stage block planning concept, which contains the 3 stages, beginning with stage 1, the assignment of slabs to the continuous casting blocks and to the hot roll milling blocks, which you can see here. The sequencing within a block and the timing and definition of the exact start and end times of the block. So the first results look very promising, and we are on a good way, let's say, really. The challenges in this project we have to face can be summarized as follows. Integrated scheduling means combining the domain-specific knowledge at the production stages The next is how to best benefit from tremendous increase in soldering performances. And there's extremely few literature on our planning problem. So research is really urgently needed. Another example I would like to show here, last but not least, is about a few thoughts about slab yards automation systems. The main goal of these automation systems could be to improve the efficiency of slab yard operations through automated handling equipment, and, for instance, also the reduction of land requirements for the slab yard systems due to the greater storage density, and on the other hand, a reduction in the number of the transporters we are using. So the typical questions are, what are the general benefits of an automated slab yard between continuous casting and the hot rolling mill? What is the impact on productivity and efficiency? And what are the cost savings, of course, through the automation of the transport and stacking equipment? And this is these economic questions are in this application the most important. So let's look at the boundary conditions and constraints we have. We have limited slab yard area, what you can see here, which is really very limited. And we have a limited slab stack height, which have to be taken into account. And the automated slab yard should be serviced here by automated rail-mounted gantry cranes, as you can see here. The cranes, of course, are also limited, and we have also the speed limits of the cranes. And we have also limits in the crane loads. And all aspects and the whole solution should be focused on economic aspects. And the solution strategy in the first step is a simulation-based modeling and analysis approach, which is used here. So one important simulation result is that the simulation study indicates that under certain conditions, these automation concepts you can see here outperforms these classical transportation systems we have and stacking systems we have running here in Linz. So this could be one possibility to really improve. And but what we have also seen during these simulations, that the use of basic heuristics can be improved, the models can be improved to go to higher heuristic models. So this is more or less a very nice case study that shows how mathematical simulations are helpful in the preparation of investment decisions in automatic equipment. Let's come to the summary and conclusions. We expect, and we can see that the human operator plays a central role with his knowledge and skills. It was in the past, it is now, and it will also be the same in the future. We have seen that automation solutions in the process industry are moving towards hybrid automation solutions. The integrated information and communication technologies enable the digital connectivity across the entire process chain. For instance, for scheduling, knowledge about our process technologies is the breeding ground for powerful innovations such as next level decision support systems we have discussed. The orchestration of industrial production plants as well as logistic and transport processes along the entire value chain requires customized, optimization systems and solutions. And finally, the most important we need is a multidisciplinary cooperation network between industry and scientific partners. So I wish you all exciting presentations, fruitful discussions during the conference, and many thanks for your attention.
Okay, many thanks, Markus, also from my side from this very interesting insights and the academic cooperations you're doing with voestalpine. And I think we have time for a couple of questions. So please feel free from the auditory in case you have a question to raise your hand or put the question into the chat. Florian Sobiecki, please.
Hello. Thank you for the nice presentation. How much do these hybrid systems incorporate mixtures of predictive models together with numerical computations? I mean, how much does modern AI play a role in putting together these hybrid?
This is a very good question, because we try to do, as you could see, we have a certain high level, let's say, on modeling expertise, and this question is typically for the discussions we are doing nearly every day, because we get in contact with these very powerful AI solutions and AI models, and yeah. We try, of course, to bring in, to connect these new technologies to our more or less physical-based mathematical models. But I can say that for typical process applications we're interested in, these solutions need more time, let's say, to grow. In terms of image processing and all these things where you have to figure out something from pictures to classify something, then these algorithms with deep learning can help definitely more. But the topics where we say, okay, we have a knowledge-based application we're interested in, we have to go in this direction more intensively. Mm-hmm. And the results seems to be, it could work, but it's until now it's definitely not clear.
Thank you.
Okay, other questions. So I do have one which is somehow related, I think, to what the last question, the topic of the last question has been. You mentioned the hybrid approaches, and we also experience in this project that there's a lot of potential in combining data science, simulation-based approaches, and optimization. We have this under the umbrella of prescriptive analytics for decision supporting, but especially in a company like voestalpine, where there's such a lot of expertise from the field of natural sciences, like material science, physics, chemistry, metallurgy. What do you think are the most promising approaches to really bring together those already acquired knowledge with the new available data science techniques, and not saying either I do it this way or I do it the other way? How can you combine this?
The problems we are facing every day are getting more and more complex. So this multivariate statistical, for instance, methods we are using really for very special problems, and we are facing here, let's say, the second order, the results behind the curtain, yeah, and not the first order. And for this, especially for these questions, we have really a very good experience to get more information about cause effect, especially about cause effect analysis. And these models run very good, from my understanding, in the online mode, pardon. But if we put these results directly into the process in online mode, then it's this step is sometimes very complicated, and you have to reduce these models more or less. So it will be the future, of course, but for this, we are together in a research with permanent contact with university, with research centers. And this is especially for these topics, we need the scientific support. Yes, this is very important, but we also need the open discussion about our domain knowledge with the data scientists, for instance. They have also come into our plants, they have to look at our processes, and they have to get in touch with our processes, of course, to understand. And if we bring both together, we can go together this way. And this is, for me, very important. And we are going this way, and I think this could be very fruitful.
Okay, thank you again, Markus. I think this was a very good closing remark for this talk, bringing together academia and the industry, which is also the main purpose of this conference. So thank you very much again, Markus, for this really inspiring talk.
You're welcome.
Okay, and we switch to the second keynote. I've heard that Professor Weiming Shen is already with us. So
Michael, sorry to interrupt you. We do have a certificate for Markus, so maybe if we want to give the certificate right now.
Okay, thank you very much, Francesco, for telling me.
Yes, I'm going to share the screen so you can announce the certificate, okay?
Okay, Markus, so here comes the certificate for serving as a keynote speaker of this conference, okay. First in virtual form, but of course you will also receive it in physical form via old-fashioned postal delivery. So,
it is perfect.
Thank you again.
Many thanks, Michael, and to all the organization team. You're really doing a great job. Many best for the conference.
Thank you.
Okay, is Professor Shen already with us? So I would like to ask him. Okay, you can already start sharing your screen. During the introduction, Professor Shen will give a talk about agent-based collaborative intelligent manufacturing in the era of Industry 4.0. And he has been working in science and industry with the National Research Council of Canada as research officer for more than 20 years before he went to China at Haichong University of Science and Technology in the role of a full professor. He was very active in the scientific community, serving as editor, co-editor, conference organizer, and chair in many relevant events, which is also shown in his academic achievements. For example, the H index of 53. All of us working in academia know what an effort it takes to reach such an H index, and I'm already very much looking forward to your talk. Please, Weiming Shen.
Okay, can you hear me?
Yeah, perfect.
Thank you, and thank you for the invitation to give a talk to this very interesting conference. In fact, I didn't attend last year's conference, but I read many papers from that conference from last year. So it's my great pleasure to give a talk here. And this work on agent-based collaborative intelligent manufacturing, I would say I have been working on it for the past almost 28 years. So, but that's the Industry 4.0 industrial revolution. We have some new challenges and new interesting things I'm going to talk today. In fact, it's also it's very interesting for me to hear the first talk, and then if it will be next year, I probably will be talking about the application of agent-based technology in that steel manufacturing, particularly the continuous casting and hot loading production processes. I'm currently working on a project on this application, in fact. But next year, I probably will be able to show you with you, but not today. So oops, I'm not sure where the. Can you see my second slide now? Looks like it's not loading. It's working. Next.
Yeah, it's working.
Oh, okay. So this is interesting slides. If you can see, in fact, I captured the screen from the web. So I would say it showed the trend on agent-based manufacturing research. So I just mentioned that I worked on it for the past about 28 years. But on the left side, you can see kind of basically it's the citation number of one of my papers. Basically, it was my first review paper on agent-based system for intelligent manufacturing, published in 1999. So you can see that the trend, which means that during the past few years, I think about 10 years ago, it was the winter time for the agent-based technology. And now during the past few years, you can see the summertime coming again, basically. So that this technology become hotter and hotter for the application of the agent technology in manufacturing. So I will mention this probably also kind of why I'm talking today. In fact, I probably during the past 20 years, I have given many talks in different conferences and in different countries about the talk, most on my projects. I have been working on this kind of project on the application of agents in manufacturing for maybe 20, 30 different projects. But today, I'm just probably will be able to show you a few examples and within that about 30, 35 minutes. A kind of outline of my talk. I'm not going to read through, but on the right side is the book I published on about 20 years ago. I think it's 2001 with Francis, and on the multi-agent system for design and manufacturing. That was the first book on the topic, but so far probably if it's only on the application of agent and systematically review the technology of agent-based design and manufacturing, probably still is the only book. But I will probably briefly talk about my view, my understanding, and of course my kind of my work on that area. So what is an agent, particularly software agents? So it basically is a concept from distributed artificial intelligence, and it's not only AI concept, but it's also from software engineering, communication network coordination theory. Why? Because I will give you a little bit of my definition later on in the next slides. And it combines several other technologies, including communication, cooperation, collaboration, and negotiation. And I will have one slide to talk about key features and probably give a few examples of this kind of features in the next slides. So what is an agent? In fact, I just mentioned that I have been working on this technology for the past 28 years, and there are many different definitions and from different perspectives. So my perspective, my definition of an agent is under the context of engineering, design, and manufacturing particularly. So an agent can be defined as a software system that communicate and cooperate with other software systems to solve a very complicated problem. That kind of problem cannot be solved is beyond the capability of each individual software system, which means one software cannot solve a bigger problem. So a number of software systems work together to solve a very complicated problem. Each software system is modeled as an agent. And some people may ask a question, so I'm always talking about software, but in many industrial applications, lots of hardware like robots, machines, and they are hardware. But I always argument that all the machines, robots, they communicate and cooperate with other agents through their software components. So that's why in my definition, I always define that agent as a software component or software system. So in the design, I just mentioned in any design and manufacturing world, in the design world, like if we have collaborative design world, and agent can be used to represent a design system, a CAD software, a simulation software, finite analysis software, even an unit database. So all different kind of software will be used during a design project. So they have to work together. Of course, different people also working in different software together. In a manufacturing environment, like I just mentioned, for example, in the steel manufacturing environment, an equipment, a robot, or maybe an AGV running in the shop floor can be represented as a software agent, and they, of course, they work together to make the kind of smooth production line or shop floor. But sometimes a group of equipment, a group of robots, they can also model as one agent they communicate. So there are different way of modeling, grouping of the systems. Of course, an agent, they are best developed not in isolation, but as a part of multi-agent system, which means that if a system only have one agent, doesn't make any sense. So a multi-agent system can be also defined as a loosely coupled network program solver that work together to solve problems that are beyond their individual capabilities. So very important concept, the keywords here is one is loose coupling, which means they are not highly coupled. That is very important concept idea, because a loose coupled system, and if one component fail, the other component system should continue to work. So I think I have next slide to show this concept. So for example, on the left side, you see I call the conventional traditional system, and one component within that system, if you pull it out, it failed to work, system will crash. On the right side is a kind of agent-based system. So they can, each component can be independently added or removed, and the system should continue to work. So it's a flat system. This slide I have used, taken from a Japanese research like probably 20 years ago. So I still use it. This shows a kind of shows the different of agents-based system with traditional system. So I probably briefly mentioned a few features of agents. First one is called autonomous, which means like in a system, and then if there are many or several agents, each one is autonomous. So in the talk, when I teach in course, I always use objects as an example. In an object-oriented systems, there are many objects, of course, they communicate or they also transfer through messages. But in object coupled with other objects. So if there is an object fail or crash, and a system still can crash because when a message passing to other objects, they may be not be able to respond. So in autonomous agent system, each agent can make decision and then autonomously and without interference by other agents. Next one, in fact, I just mentioned that it's very interesting from the previous talk. You can see the three words: reactive, proactive, and adaptive in the manufacturing environment. So I probably briefly mentioned that one in a little different example. It's a typical one when earlier we worked on that feature is the N-unit database. A typical N-unit database in an N-unit design or N-unit environment is reactive, which means a database is being used to save data when maybe receive data from the system. And we can develop a database, a proactive database, so that the database becomes smart enough that if you need the data it will automatically send to you in place, particularly in the NUnit design environment, because a data file, even though with high-speed internet today, but sometimes a data for NUnit design, even for project, not only megabyte, maybe terabytes data needed to be transferred from one computer to the other computer. If a software needs that particular data set of data, and after you make a request, it may take hours for you to receive the data, and so that you can continue the design optimization work. But if a database becomes proactive, so that the data will be transferred, because the database is more as intelligent agent. It's monitoring the design environment. So there is one computer with, of course, one designer and need a database. The database, proactive database agent knows that you would need that particular data set in let's say in a few hours, and so the data can send the database agent can send the data to your location when you need that particular data set. It's already there in your place. That's a typical example of when I use in a like a design environment. But in the steel manufacturing example, like the just mentioned, and in the proactive situation, which means that a system can make proactive, take initiative to make a decision instead of being reactive to any failure environment. So of course, adaptive, even more advanced, you can see, because the system with that particular agent or system can self-learn during the process. So it's become more and more intelligent. That will be the future of the agent-based system. It's a cooperative and a collaborative. Of course, all the agents, as mentioned, they have to work collaboratively in order to solve very complicated problems. Dynamic and fault tolerant are very important in particular in let's say steel manufacturing, in other manufacturing environment, because the system, as I just mentioned earlier example, the system are always dynamic. If one component, one machine fails, the other system should continuously work together to solve the complicated problem. Will continue to work. So that's the kind of first one of the first project that I worked on. We called intelligent shop floor, so shop floor. And in fact, we defined this kind of shop floor and intelligent shop floor based on internet, web, and agent technologies. We published our first paper, I think it's 2006 in IEEE transaction. It's focused on the implementation of distributed intelligence, particularly distributed agent-based planning and scheduling in manufacturing shop floor. So that's a kind of shop floor environment in our research lab. Basically, we have a few machines, and then the task needed to be allocated to different machines. So in a traditional, typical scheduling environment, basically a production planner or a shop floor manager assign job to different machines. So that's assignment of jobs. In an agent-based manufacturing environment, the scheduling is done through negotiation. Basically, at the shop level, there is some kind of request for jobs. So we usually call it request for jobs to different machines. So different machines can submit their bid, basically based on their availability, their capability, and then there is one kind of manager, one kind of agent and coordinator will, based on the bids received, and then assign job to different. So it's kind of a negotiation approach among different machines. This was implemented in a digital shop floor environment. We like about 15 years ago in our research lab. It's a very early project. That's kind of a schedule on the web. Probably I just mentioned in that particular, that slide about the digital twin technology. The first speaker also mentioned in his talk today. That was a part of digital iShop floor, eShop floor project about 15, 16 years ago, and the paper was, about 20 years ago. The paper was published, in fact, in 2002 in Communication of ISM, and we called the Java-based 3 Java 3D enabled cyber shop workforce. So why was that? In fact, it's mostly on the digital twin, but I want to mention a little bit here under the agent-based technology behind, because they also the collaboration among digital twin and the physical twin, and of course among the different machines. So why we had this project? It was the idea of the machines, let's say, particularly during pandemic. And we have a machine in China, in Canada. It stopped working for some reason, but the local engineering cannot figure out what's wrong. And we probably will need to call an engineer from Germany, from Italy, from Japan. He made that company made the machine, and then to come on to repair. But in the pandemic situation, that cannot happen. So with this technology, like we had about 20 years ago, basically, we called, of course, that time we didn't call it digital twin, but a virtual model of the physical machine, exactly identical to the physical machine, with the kinematics of dynamics of the machine, so that the remote engineering can check out on the web to see what's inside, what's wrong inside of the machine, help the local engineer to fix the problem in a local environment. So that one, there are two key things on the collaboration behind. One is, of course, the collaboration between the virtual and it's more on the real-time synchronization. On the other hand, of course, different machine I probably mentioned in my iShop follow-up. I'm not sure I can run simulation here. That was the one project also I mentioned that I worked on about 20 different projects on the application of the agents in manufacturing environment. That was one project that we worked on in a real shop floor. So there are 4 vertical machines, and it's an integrated system. And if you one machine, even the AG, I think I'm trying to run it. It's running here. I'm not sure you can see it. Even the moving card in the middle. So any system, subsystem fail or stops, the whole system needed to shut down. That was the situation before we worked on this project. So the idea to implement an autonomous agent-based system is to model each machine as an agent. Of course, also the rail card in the middle as an agent, so that they can work kind of autonomously or independently. In case one machine, even as a lower card fail, will be very much difficult because it cannot transport. But particularly for the 4 machine, each machine fail, maybe the tool broken, and only that particular machine, because they are loosely kept. So each machine can stop and the other system can continue to work. Even other 3 machines can maybe negotiate to see who can finish the work initially was assigned to the machine that failed. So that's the one project, and we finished the deployment, the development of the concept and the system. And the company, of course, they implement a kind of loosely kept system so that 4 machines can work independently without intervention with other machines. Next, this one I won't have too much time to. This one even more interesting, probably, even though the picture of diagram may not show very well. That is one company on the manufacturing of the trucks. So that, in fact, this was done in Canada. In fact, because the order of trucks, as you know, probably in Europe or in Canada, with only 1 or 2 trucks. So each truck in the production line is different from the truck before and after. So an automatic painting shop for the truck painting is very difficult. So that one, so what they do, in fact, during I think about 10 years ago, that project was running to trying to implement an automatic painting shop with several robots. So, but each robot can fail. So that this company had a solution to have one basically worker painter, which means he needed to wear the clothes. It takes about half an hour to wear the clothes on and waiting in a kind of standing by room. Just, of course, during the early stage of the
like context. I'm not going to talk about.
There was some noise over there, so I try to finish. And if one robot fail, and then because during the early stage of the implementation, the robot can even fail more frequently. So the painter can move in the shop, move in the painting shop and finish the work which initially assigned to the failed robot. But we developed a kind of autonomous, which means the decision, of course, not only the scheduling, but also the path planning for all the robots. So just in case the one robot fail, other 5 robots, they have to reorganize to finish the job initially was assigned to 6 robots. That was a kind of mechanism of agent-based kind of dynamic fault-tolerant approach we implement in the particular shuffle. Another shuffle agent planning schedule, I won't have time to get into too much details. But what I want to talk today is because all the work, like I mentioned before, is mostly the work I have done in Canada, maybe between 20 and I was 10 years ago, from 2000 to 2010. And today, because talk today is the agent-based collaborative intelligent manufacturing in the era of Industry 4.0. Not only Industry 4.0, we have the new technology like Industrial Internet, or IO, Internet of Things, big data, cloud computing, edge computing, all kinds of technology come out. Hopefully you can see briefly a picture on the right side. So the agent-based technology really is kind of in the middle of other technologies. So for example, IoT, Industrial Internet today is really provide a much better environment for data collection, real-time response for the real-time event. When we worked on 20 years ago, even though we worked on the wireless sensor net for data collection and real-time feedback, but it was very slow. Of course, it's with very error-prone kind of approach. And today we have the edge computing, particularly not only cloud computing, so that we have lots of real-time decision making algorithm can be implemented on edge server instead of in the physical and at the machine level, because the computing power may not be enough at the machine level. But if you send all data to the cloud, the decision-making process may be too slow and reaction will be very slow. So the edge computing technology today can provide a much better environment for agent-based systems, or implementation of agent-based technology in a real-time manufacturing environment. Blockchain technology, as probably most of you are aware, that it was a technology hot during the past few years. And in fact, one of my students also tried to implement blockchain in agent-based manufacturing environment. The argument was because agent-based technology has some disadvantage on the security and issues. So blockchain may be able to provide a good alternative for solving, to address the security problem. But I would say the conclusion was that blockchain is not the good technology for real-time agent-based manufacturing system. Of course, blockchain is a good technology for banking system, for supply chain, manufacturing system, which can also be implemented on agent-based approach. But it's not good for agent-based real-time environment, because blockchain will make the system very slow and probably not responsive enough. So I have already a kind of 20. I probably spend the next 3-4 minutes or 5 minutes to explain what I can see today on the application of agents and other technology, including digital twin, IoT, and big data in collaborative manufacturing and in today's Industry 4.0. So I can see at 5 different levels. During the past 20-some years, 28 years almost, I have mostly working on if you can see my examples on the 2nd level, or a little bit on the 3rd level. In fact, all 5 levels are good application of this technology. I had one slide, I didn't explain agent-based production planning and control project is on the 4th level at the machine level. So the components with consensus in the machine level needed to work collaboratively to improve the efficiency of the machine and also improve the quality of the machine, particularly for real-time response of the let's say the information get from the sensors. Second level is really the examples I mentioned on the agent-based planning and scheduling of shop floor level for real-time process planning and scheduling, and just the time as material handling. That example I didn't have time to explain it. It was an example with a project that we worked on GM, General Motors, on the agent-based material handling for the delivery of materials in the shop floor environment. And the third one is the energy efficient manufacturing process. In fact, that is the project I'm currently working on the steel manufacturing products process, which means we consider both the energy efficiency and the resource efficiency in that continuous casting and hot rolling production process, as the first speaker mentioned, because the how we can effectively use the energy, heat energy in the slab, and then during the process organize not only save energy but also optimization manufacturing production process. It's very interesting application of this technology we are currently working on. And at the enterprise level, I think about 10 years ago, we usually used a term called virtual enterprise collaboration. Today's world, probably we more talk about the supply chain, value chain at the enterprise level. So co-involvement of suppliers, OEMs, and also customers in the same environment to improve the efficiency of the whole supply chain. But at that level, I told my students and as some of my the people who want to, it's difficult to validate, we implement a kind of, if you only work on the PhD thesis one project, only when you really work with the several companies, you can really implement, because first level, on the machine level, shop floor level, for graduate students, they are good example, and because they can develop validation, demonstration validation in shop floor, at the shop floor level. Third level, it's difficult to do this kind of validation. And third level and fourth level on the supply chain, it's difficult to validate because you need several companies to be involved and system to be implemented for this kind of validation. In fact, the fourth level, I call the after sale service. Some people also call the smart product with service oriented business model for product service. This is very interesting and become more and more interesting field for business, because in the past manufacturers they manufacture the cars, whatever, and equipment, they basically sell the equipment cars to the end user. But in today's world, and the manufacturer will also provide active service to the end user. So this kind of approach become to provide proactive maintenance service, because it become much more important today. And agent-based technology can provide a really good fit for the implementation of this kind of service. I think I'm running out of my time today, so I'm going to finish with my last slide on the conclusion remarks. So the emerging technology like digital twins, industrial internet or Internet of Things, big data have become the most active R&D area today. And in fact, this kind of technology, I call them, they bring new life for artificial intelligence and for agent technology. In fact, I don't see, like some people could say we have new artificial intelligence with new AI. In fact, I don't see new AI. I see the imaging technology like the digital twin, IoT, big data, really bring a new life for artificial intelligence, for distributed artificial intelligence, and of course for the aging technology. And then in fact, then this technology are moving to be more practical. So collaborative intelligent manufacturing basically is application of the technology I just mentioned, is among the most significant application area for this kind of technology. And in fact, like I personally, I worked on in this related area for the past 28 years. So there are mature technologies, agent-based technologies for deployment. but still when we move into the real in production, a real application, industrial application, just like the steel manufacturing industry, there are still significant R&D, particularly the development effort requirement, because as the first speaker mentioned, in real applications, the situation is much more complicated than we do in academic research world. So lots of research and development effort are still required. And also I mentioned that the security privacy issues are always the major challenge for industrial application, and the security and privacy of the information, whatever, are very critical for industrial companies. So that's needed to be addressed. Otherwise, nobody will apply or deploy this kind of technology in their company. I think I have to stop here, and this is some of you already know that that's the journal where we launched 2 years ago in this tech related collaborative intelligent manufacturing node. Thank you for your attention, and I'm not sure where I have time to take a couple of questions. Thank you.
Thank you, Professor Shen, for your overview about the many facets of agent-based technology. So we do have some time for questions, and I would like the audience to simply raise a hand in case you have one. So then I will take the freedom to start the question session. When you explain the main characteristics of agent-based systems, the very first point you mentioned is that they are autonomous. But on the other hand, they have to be collaborative. So what do you think the proper degree of autonomy is, or does it depend on the application if the cooperation is steered in a reflective way ad hoc, or if it's a central control panel that somehow orchestrates the way the agents cooperate?
Thank you for this very good question. Depending on applications, in fact, I mentioned 5 levels, and probably talk about one level in the middle on the collaboration among companies. So at that level, and both can happen. Autonomous means that one company involved in the collaboration among companies, so that company can really make autonomous decisions. For example, one company publish a kind of cohort bid. I have this kind of job that needs to be done, and which company is willing to take the job, and they provide the bid. So that each company can really make autonomous decisions, said, even though I'm very busy, I'm already run 3 shifts, 25 a day and 7 days a week, but money, so I can submit a bid, and then I want to get the job. So it's little. With some company may not be the case. I probably, if I run in the operation, I take the bid, I may probably even waste money for something. So the decision really can make autonomously at the company independent company level. So that the case is kind of I call autonomous decision making, mostly in that level. And of course, if you have several companies to be involved, for example, in the supply chain, it's more on the collaborative level, not really on the too much you can make it autonomous level the decision because it's related to your own utility, your own profit, but you still need to be in collaborate with other companies. Otherwise, you will be out because nobody will be working with you. So that's the company. At the shop floor level, it's like because they are mostly not really so loosely kept, so that autonomous decisions can make, but mostly more on the collaborative manner. And it's really depends on the applications. You had a very good point. Autonomous and collaborative needed to be in some kind of depend on the applications, but also needed to be in complementary public.
Okay, thank you very much. There comes a question from Francesco Longo, please.
Thanks a lot, Professor Shen, for your very interesting and clear presentation. I have actually a question, even if my question is not strictly related to your presentation, but as Professor Affenzeller was mentioning when he was introducing you, you are a very well-known and international expert worldwide. Your H index is very high. We do have, as part of our community, young researchers, and they are always struggled, you know, between publishing different papers and from the other side try to increase their citations and so on. Even sometimes the university career push you to publish a lot because publish or die, sometimes we are used to say. Which could be your suggestion for young researcher working in this area in smart manufacturing, Industry 4.0, to find a good balance between, publication and visibility on Scopus, Google Scholar, and so on?
It's not technical, but it's a good question. So how I can do, basically I do myself. Probably good advice probably will be the one I usually give to my students. And for different students have different objectives. Of course, if they go to their goal is go to companies, they probably don't pay a lot. But the question you have is mostly for research, and they want to become a research in the academic world. So for the publication, how you can publish more, you have to citation to different. Publishing more is really, I think you have to not only do a good job, you have to abstract kind of your research results into a level that which means yes, you didn't do the good job, you have a good application, particularly for engineering students, but you need to write in a paper in a way that the technology you proposed, you develop, you implement can be applied to similar field, similar application, not only to the particular that project with level. Otherwise, your paper cannot be published, and otherwise your paper will not be cited by others because your paper, your work only related to that particular problem. So no other people may not see the value for other applications or other field. So this is the kind of advice I usually give to my students. So I repeat again for hopefully that it become important point. So when you finish a project or a job, you need to try to abstract the research at a high level. So that the technique, with the method, with the things you develop, proposed, which can be applied to other similar applications, even in other fields, so that other researcher or other people can learn from that one and apply. And then your work, of course, can be will be cited by many researchers. So that is one advice I usually give to my students. Of course, for the elite senior researcher, you want to publish more, get citations, I would say I was the mid-level researcher. You already had assistant professor level. As I would say, you publish a good survey paper, review paper. Of course, you get a good citation because many people want to see the review paper. Of course, it needs to be a good review paper. I just reject a review paper today because it's not really a good high-level review paper. And second one is like you, Francesco, and other people. You have to in a kind of academic research committee. You organize conference. You organize special sessions for the conference. You organize special sections, special issues for journals. So you get to know by other people. So that because you get to know by other people, of course, other people will read your papers, of course, also cite your papers. So that's I had two advice for different level. First one is most for students. Second one most for junior or younger researchers. Hopefully that kind of advice help for some people.
Thanks a lot. I feel that your suggestion could be very good both for students and young researchers that are approaching this career. Thanks a lot again.
Okay,
thank you.
We have one more question from Florian Siwiecki.
Yes, thank you for the nice talk, Professor Chen. I would like to know, is there any connection of ongoing research in these agent-based systems with mathematical questions from the theory of cellular automata?
That's a good question. It's not a new question. It was a question I would say 20 years ago I asked, and then we had a professor working automata and also working and trying to work together. And I think the idea from the automata world can be learned, applied in agent-based world. That was initially about 20 years ago we trying to do, and so hopefully that. Not directly, but kind of indirectly answer the question. It's possible to learn some approaches from one side to other side, not really together. But the second point, because at the beginning of your question, I thought you were talking about the mathematical approach and also the agent-based approach. Because agent-based approach is really distributed artificial intelligence, so it's a kind of symbolic modeling approach. It's not a mathematical approach. And also I would say maybe 15, 20 years ago, I tried to work with professors who are really good on mathematics to try to combine things together. In fact, in the agent-based planning and scheduling world, some kind of application are feasible, are possible, but they are really very much two different approaches. So the third one point, probably also want to mention that not pure mathematics. For example, like some people working genetic algorithms, like a machine learning. So this kind of two approaches can be very well combined in I don't have time to explain in details because I have a few papers on the integration of agent-based approach. It's more on the collaboration negotiation approach with genetic algorithms for the manufacturing scheduling programs. It's possible, and then you can see two different approaches trying to combine together, because one is mostly for global optimization, and agent-based approach is not really for, I would say, it's not usually for the global and static optimization. It's for a quick reactive, quick response to the dynamic situation, and for trying to find a compromise or good enough solution for the real-time environment. It's not the global optimization approach. So if you can try and combine two approaches, and then you probably can find a compromise solution in some applications. That's probably one question I try to answer in 3 different ways. Hopefully it helps.
Yeah. Thank you.
Okay, thanks also from my side for all the interesting answers of the questions. I think there's no more hand raised, so I would like to ask Francesco for assistance again, because I'm sure we will also have a certificate appreciating your keynote talk, and here it is already. So thank you very much from our side, which is shown with the certificate of appreciation, first in virtual form, as mentioned before, but also in physical form. It will be delivered to you. So thanks again very much. Also,
thank you, Professor Shen, again very much.
Thank you. Bye.
Thanks also to the audience, and also for the interesting questions. And we see each other again in the parallel sessions after the lunch break. See you then.